Yeah, thank you very much. And I would like to start my talk thanking the organizers for putting this together. This is the second meeting after Ingelheim in this kind of SPICE setting. I enjoyed very much. I learned a lot. The only question I have, why did I get invited? I was thinking myself, because I have no minimal model and I have no long tables, so I question myself. And the only reason I could found is because I wrote a year ago an article about unconventional magnetism. Probably Libor has some issues with this, so maybe what we wanted to say, you too, sure. We can discuss this. We can discuss this, of course, with a glass of wine. So basically, what we wanted to say, of course, I was forced to write this article by the Nature editor, yeah, forced. Yeah, yes, I was forced. The story was like this. The Nature editor asked me at the ICM to write this article, and I said, I just crossed the hall. It was actually Thomas Jungwirth. I said, no, please ask him, he is the best person to do that. No, they want to have a non-Mainz opinion. So therefore I had to do it. Of course, I do not know too much about spin groups, so I asked Jiang Liu to help me. I met him accidentally on the conference, and we wrote it basically instantaneously. No, but the message of this is basically that unconventional magnetism, and probably you all know that much better than me, unconventional magnetism is something where we have a compensated magnetization, which is symmetry enforced, and at the same time we have some spin splitting in momentum space. And then you ask which kind of properties you want to measure, and then you use your group symmetry machinery to spit out which elements have that matrix element for a second harmonic generation or whatever you want to do. But that's not what I'm talking today. I only want to remind Libor that we have to continue on these discussions, and I think he didn't tell me exactly where I'm wrong yet. So let's continue. Today I talk about magnons, and this work was done in a collaboration with people, and the most important person is Weshdan Beda. He is a graduate student who did most of the calculations, and you will see I use a heavy machinery for doing this, and for this we need experts developing the methods, and this is shown here. They are listed here. And I profited from a lot of discussion with experimentalists, especially Yixi Su, who is an expert on neutrons, and Nicolas Biniskos, who is an expert on RIGs. And simultaneously, at the same time, we did this work. Manuel dos Santos Diaz did a similar work, but using DFT, while we using many-body perturbation theory. And there was a lot of discussion going on. And the stuff I'm talking about, you can see in these three papers. All right. When you go to this neutron scattering community, you talk about chiral magnons, and that is the title I used. They asked me, what is that? And basically, that is just so to say, different community have different words for the same thing. So often you see in that community circularly polarized magnons, where we're talking about chiral magnons, but it's basically the same thing. If you have a dipole in an external B field, you have a Larmor precession, and this this is a differential equation first order. You basically have a Larmor precession, and the rotational sense is basically determined by the Larmor constant. And for electrons, this is negative. So some nuclei, they are positive. But what you get is then a counterclockwise rotation of the magnetization in the external field. And the neutron scattering people call this circular polarization, and we call this chirality. And if you put, of course, interaction into the system, you get spin waves, that we call magnons, and we call them circular polarized magnons or chiral magnons. And you see here that these are different words used simultaneously in different communities. This is more neutron scattering community. Also, Gerrit Bauer probably never saw a neutron. Saw a neutron, but probably never worked on neutrons. And basically, so I continue with this word chiral magnons, but you should think of a a circular magnon polarization. And so how does this fit now into the context of the classification of ferromagnets and antiferromagnets and altermagnets, where we have broken Kramers degeneracy or Kramers degeneracy in momentum space of the electrons, and this typical D-wave splitting here in this particular cartoon. And this has been worked out by the gang here. The first author is probably Libor, and they are probably somewhere Thomas and Jairo and some other authors in between. And what you so basically what I have showed you in the ferromagnetic case, you have this quadratic spin wave dispersion, and you basically have a chiral mode because the magnon is the magnetization is rotating in one direction. And if you have an antiferromagnet, then you have two degenerate modes. Basically, you have circular degeneracy of the two modes. And if you have now the altermagnetism, you should have a chiral magnon splitting. You should have an anisotropic dispersion in certain directions, and you should have a chiral magnon splitting at certain Q vectors, magnon Q vectors. All right. And the idea is to find this and actually to use this magnon magnon splitting. So now when we think about magnons and think about, we want of course to study these magnons in certain materials, and I would say there are a few different communities. So I'm coming from a spintronic community, and when I talk about communities, you know, in solid state physics and condensed matter physics, you have wild materials, you know, 5 components, this and that, you know. But if you think about devices, then you want to minimize entropy. And you realize even today we work with silicon, we work with graphene, and the furthest we go is maybe gallium arsenide, or maybe for a topological insulator we take bismuth telluride. So actually the number of materials which we use in a device is actually very limited. And so in the spintronics community, we have some requirements on materials. Say, for example, we want to have high spin polarization of the conduction electrons. We want to have long spin lifetimes and long spin diffusion lengths. We want to have high Curie temperature, and there are many others. We want to have great spin to charge conversions and so on. I don't list all. There's another community, the magnonics community. The magnonics community wants to manipulate or wants to transfer information through magnons. And of course, they are dealing with systems which have very low damping, high spin wave velocities. They want to deal with high frequencies. In order to have low damping is low spin orbit interaction, and you want to deal with tunable magnetic anisotropy. And the list is, of course, a little bit longer. And so therefore, this community is very interested in insulating materials, while this community is very interested in conducting materials. So if you think about materials in this context, so I restrict myself to very simple materials, two-component materials here for the conducting materials, and I have chosen the some of the nickel arsenide structure, whereas for the insulating materials I have chosen some rutiles, which you see here. And of course we want to measure this these magnons, and we have two basic, for bulk magnons we have two basic tools. One is the inelastic neutron scattering, and the other one is RIGS. And for neutron scattering, you know, the lower the magnon energy, the better, because most of our reactors are thermal reactors. The neutrons are thermal neutrons, so we cannot go high up in energy. Of course, in the US you have the spallation source, and typically they have a resolution of 1 millieV. Whereas in RIGS it's the opposite. The higher the energy, the better, because so to say you have a resolution of 20 millieV. But if this 20 millieV is on top of maybe 150 millieV, then you still have a good resolution. And now if you think of the Curie temperatures of these materials, so these rutiles have about 50 Kelvin, and these transition metal pnictides in the order of 700 Kelvin, then you can understand that the magnon spectrum of the rutiles is probably very low, and it's a good case for neutrons, whereas for the transition metal pnictides, it's 700 Kelvin, and it's probably better for RIGs. So I'm moving on with reminding you what is a magnetic excitation. And basically, you have to deal with two different excitations. One is the magnon excitation, a collective mode. And the other one, of course, is the single particle excitation, basically a spin flip excitation. And now the spin flip excitation basically provide a continuum of excitations. And now it depends very much where this, so to say, where your spin up, spin down energy difference gap is, where this Stoner excitation starts. And in insulators, typically you have a huge band gap. And these huge band gaps helps you to have very, very nice magnon modes with very, very little damping, and therefore it's so good for this magnonics community. Whereas in metals, of course, you have conducting electrons, so basically you hardly have any gap in the Stoner to reach the Stoner criterion, and therefore you have a lot of damping of the magnon modes. So when we do that, when we investigate this computationally, typically when we have these localized systems, localized moment systems in the insulators, it's good enough, you know, to do an ab initio calculation, calculate these Heisenberg parameters, put these Heisenberg parameters in the linear spin wave theory, and you get your magnon spectrum. If you deal with metallic systems, the situation is different because you have to deal at the same time with it-inerrant electrons, and therefore you are calculating the magnetic response function, where you basically treat single particle excitation and the collective excitation on the same footing and simultaneously. Basically what we calculate is this many body perturbation theory, the susceptibility, and we calculate, and the poles of the susceptibility gives us the excitation. So for example, if you make a cut in this frequency over Q vector plot, you look at this susceptibility and you see maybe a very sharp peak with a certain width, and this is your lifetime of the magnon mode, and you see a broader peak, and this is your Stoner excitation. And sometimes, you know, this moves into there and it becomes very broad and things like that. And the way we do that technically, it's basically an extension of what we call in density function theory a GW approximation. It's actually what we solve as a beta sub beta equation, because we interpret the magnon as a coherent superposition of occupied majority states and unoccupied minority states, and vice versa. So basically the response function is given as the variation of the magnetization with respect to the B field, and the magnetization is expressed by the interacting Green's function, and the interacting Green's function, and the derivative of the interacting Green's function, the interacting Green's function can be related to the non-interacting Green's function with the self-energy, and for the self-energy we take a certain approximation, which is the GW approximation. It's a common approximation in that field, and this gives you basically the beta sub beta equation where you have the Stoner excitation and all the coherent approximations, coherent interference terms. Now I'm coming to the material set. We first look at rutiles. So we look at manganese fluoride and cobalt difluoride, and there's some technicalities. We use a certain LDE plus U, and we have magnetic moments here. And as I said, the Curie temperature is very low. Therefore, I think this is a case for a neutron scattering. And the question is, can we get a chiral splitting that is large enough resolvable in experiment? So therefore, before I do this magnon calculations, I was thinking, let's look first at the electronic band structure. How large is actually the splitting in this material? So you have here cobalt difluoride and manganese difluoride. So you have a 3D and a manganese has a cobalt has a 3D orbital which has no node, and Fluorine has a 2p orbital, which is also no node. Everything is super localized. You don't feel very much from the crystal field. So therefore, also your splitting is very small here. So the splitting, of course, occurs only in certain directions. Here it's M to gamma and A to Z. And you see here, so the splitting didn't thrill me. So I moved on to manganese fluoride, and you have a magnetic moment is about twice as large. You have a larger splitting. And what you also should know, you have a gigantic band gap. And is this the material to go? So we need more crystal field, we need more larger splitting, and therefore I thought maybe we should go to cobalt chloride, dichloride, or bromide. You go here in the periodic table down, so the wave functions become more delocalized, and the magnetic moments are still very stable. And what you see indeed when you go now from the fluorides to the chlorides to the bromides, you see here the splitting is increasing. And so then I called my friends and said, you should prepare this cobalt difluoride, and this cobalt bromide is much more promising than this cobalt difluoride or manganese difluoride, but unfortunately there are problems. The growth of these materials are very difficult. Usually they want to be in another phase. So considering this, I told my students, this is all too small, we give up in this direction, we stop. As soon as we stopped, McClathy came out and put a paper on archive, and he measured actually this manganese difluoride. But for me personally, this is a crazy experiment. I mean, a wonderful experiment. I should say that this manganese difluoride has a prehistory. There are two other papers also by neutron scattering. I think one paper was submitted and then retracted because they haven't been sure anymore. I tell you what is the story. So basically this is the experimental measurement of the magnon dispersion, and we focus ourselves on this line here, roughly between gamma m in this direction. And what you see, the overall energy scale is about 6 millieV. And then you see here the measured, so this is from these measurements you can you distract Heisenberg parameters, and you can also recalculate the thing, and you see here the splitting. That's the splitting we are talking about. The splitting is very tiny. And you see here the splitting in a larger measure. Here is gamma m gamma. So the splitting is here, and you see the splitting is about 0.2 millieV. It was measured. That's huge for neutron scattering, right? No. You can measure macro EV. Yeah, but not with polarization analysis. Yeah. It's quite, yes. And they also did the polarization analysis, and then you see, I mean, the data are, you see some scattering in the data. And then you see they also characterize the chirality of the different modes, and you also saw the chirality splitting. This is a very, very good experiment, and I wasn't sure. I will give up too early. That is.
Could you maybe explain? Is this a gapped spectrum? Why is there a gap?
There is no gap. I think this is so we are focusing on this splitting.
Yeah, at gamma.
Yeah, okay. So sorry, I did not explain all the details because you are so deep dipole fields, and these dipole fields on this level of energy, you have to subtract. You have to worry about dipole interaction and things like that. Yeah.
Sorry, question. So basically, this is the splitting between the two chiralities.
Yeah.
Right. So why do you need polarization analysis? You know, if they're split, they must be chiral.
They are experimentalists. They want to prove that. Yes. Yeah, I know. But you have probably in experiments you can have many splittings. You can have there are dipole interactions involved, there are domain walls, there's blah blah blah. When you read this paper, but you have to exclude everything to make sure that it is really that.
Sorry, Stefan. Stefan, one question. Are you also going to discuss the other papers that they don't see that?
No, I don't do this.
Okay, because PSI, Oksana Saharko had really very, very high resolution data, and they didn't see any splitting.
I know.
So that's controversial.
But you know,
right?
I'm not in the position to criticize this experimentalist over that experiment.
The one you like.
No, I didn't take the one I liked. I did take the one which was recommended to me by the neutron scattering people. But they analyzed the 3 papers and told me that is the thing.
I mean, they're both very good experimental groups, right? So
Yeah, they are. You know, I'm not in the position to judge an experimental group. You know, yeah.
Exactly.
But I think I know that there are 3 works. I think one has seen it and I think retracted the paper. One, Oksana, has not seen it, and McClarty had seen it. Yeah.
So the gap, I think, but Floyd, the gap is because that's it's an easy access antiferromagnet, right? Is that correct, Vladimir? The gap at
You know, we're talking here about 1 milli eV. You know.
yeah.
Yeah.
Who are the neutron? Because Paul McClarty is a theorist. So
I mean, I think.
that's the one I know.
Yeah.
The people for Saclay, and Oksana is as PSI.
It's a Oksana is PSI, but this experiment was done, I think, at ILL.
Yeah.
Yeah. So I should have said maybe I'm a little bit biased because in the department which I am, there's another floor, and they are sitting the neutron scattering people. And they were totally excited about this work, and I try to understand what is the difference to the other work, and they can understand from all this analysis that this was very rigorous. Yeah, but I do, you know, Oksana's work is also nice. I'm not able to judge it. I only took it because it is really small energies, and I think what they are very proud of to having the polarization analysis on the level of an 0.2 millieV, because for this you need a particular flux and things like that. I'm sure, you know, this is science. You know, it will be remeasured. We don't have to worry. It's only a question of beam time and applications and yeah.
If I may, that it's on a level like saying in RPES, we see the splitting of the bands, and we do spin polarized RPES, and now we see it's an altermagnet. It's on the same level.
Yes.
So you would say, who doubted it? But still.
All right, I will move on to these the conducting ones, the metallic ones, the transition metal pnictides. So we investigate in totally 4, I think, and they are listed here. The most popular one is chromium antimony. Chromium bismuth doesn't exist yet, but it can be grown. I think chromium arsenide exists, and vanadium antimony also does not exist, but can also be grown and is currently being grown. So I should have said we switched from the fluorides and the chlorides and bromides to other types of systems which are also nickel arsenides and have larger splittings. The sulfides, for example, do a better job there. And basically what you see is the magnetic anisotropy is listed here. You see all of them are out of plane. You see the energy difference between the ferromagnetic and the antiferromagnetic states. So all of them are antiferromagnetic. They have an orbital moment which is larger if they have a lot more spin-orbit interaction. The magnetic moment is in the order of 2 to 3 Bohr magneton. These parameters are also interesting here. And then, of course, we can look at this typical band structures. This one is a non-relativistic band structure. Of course, we have also a relativistic band structure. And you see that for vanadium antimony, antimony, it is the splitting is smaller, while, for example, for arsenide and bismuth is larger. And also, you see the splitting a certain high symmetry, certain lines here in this system. And of course, you could argue that it goes somehow proportional to the magnetic moment, but that's not true. You cannot scale it with the magnetic moment. It has to do with the crystal field. I should also say that you can, so to say, determine this, so to say, the energy difference between the splitting energy, and the splitting energy here is listed here. So it's the largest splitting energy, and the splitting energy for chromium antimony has been measured to about 1.25, and in our case it is. Experimentally it's 1, in our case it's 1.25. Then the next thing is, so we have looked at the band structure, we confirmed that it's an altermagnet, we have different splittings for different systems, and now we look at the spin flip excitations. And if you first look at the Stoner excitations, so basically this is the spin flip excitation from an occupied majority state to an unoccupied minority state and vice versa. And then you see we look at two different directions. One direction in which the splitting is forbidden and one direction where the splitting is allowed. And you see where the splitting is forbidden, you have a Stoner continuum. The Stoner continuum has a certain width, a width of a few EVs. And you see both chiralities are basically identical. You see the different chiralities as minus plus and plus minus in the susceptibility. And so basically we go here and you see if you're in the other direction where it's permitted, they are not exactly identical. So you have a chiral splitting in the Stoner excitation. It is small, but it's visible. And you know this is different positions along the line gamma L. Different Q vectors at gamma L. So now we look at more at the magnon excitation. So you see here again we go in a certain direction. Gamma L is the direction where you are altermagnet active, and there you have a direction where you're not altermagnet active. And you see depending on the Q vector, you have first a very sharp peak, which is not very sensitive to the chirality. But then when you move into the Brion zone, or along the high symmetry line, you see the chiral splitting becomes larger. And the amplitude of the response also becomes different. So you see here, first of all, the peak becomes broader. You have a chiral splitting. The chiral splitting increases. And then at the end, when you go back to the high symmetry point, the chiral splitting disappears. But it's also you see the difference in the amplitude. Whereas in the other direction, of course, you see nothing. And so we looked at this. This is basically now the magnon dispersion along these high symmetry lines. And you see, first of all, this is the gamma point. What you see is basically when you go along this line L gamma or along AM, you see at the very beginning the chiral splitting is very small, but there are Q vectors where the chiral splitting is fairly large. The chiral splitting here is in the order of, I don't know, maybe 60, 50, 40, 50 millieV. And then you have you can analyze, you can compare also with experimental data. For example, you can measure the spin stiffness, and the spin stiffness in different directions is different. And experimentally, we have about 266 millieV per angstrom, and theoretically, we have between 200 and 175. So we can compare this now with experimental data. These are the RIX data recently obtained. So of course, they have also resolution problems, and they have also we wish to have more points here. So put it this way. Somehow, so this is not a numerical issue. So we tried very hard to understand what this is. It is a feature of the band structure. And you see we have unfortunately only one single point here. But here the splitting is very large, and they cannot determine the chiral splitting. Yeah. And here you have the neutron scattering experiments, and these neutron scattering experiments agree fairly well with our results. These are the 260 millieV which I showed before. So now, in parallel, Manuel dos Santos Diaz did DFT calculations. And what we found out is, when you look at the band structure, you have just a pseudo gap here. You have here chromium states, and here a chromium majority, minority, bonding, anti-bonding states, and your Fermi energy is just here. Now the problem is, if your sample is a slightly off stoichiometric, which happens easily, as these experimentalists told me, because the melting temperature of these materials are very, very different. Then if you have a slightly difference in the stoichiometry, you can move your Fermi energy a little bit due to the self-doping. And that means that this magnon dispersion is varying. So that a small change of 30 millieV in the change in the Fermi energy will significantly change already the magnon dispersion. So in order to get this in line, one has to understand very carefully what is geometry. But of course, they do EDX, but this is not the bulk measurement. All right, so what we also looked at is, so to say, the lifetime. Basically, we look here at the lifetime broadening as function of the Q vector. First, you realize at around the gamma point, the lifetime broadening, the damping parameter, is proportional to Q square. And you have here a damping parameter, and these are the damping parameters in the theory, and this is the damping parameter in the experiment. Oh, sorry, this is messed up here a little bit. Then you see that the damping is very, so to say, varies a lot. And you see here the damping of the chiral and the different chiral rotations, or the different chiral directions is different. You see here a relatively large damping of 40 millieV, which goes then back. And here you see a large chiral splitting of the chiral damping in this material. And so this we have analyzed for the chromium antimony. We have analyzed this also for all the others. In particular, this vanadium antimony has a very interesting feature. If you look at the magnon dispersion, you basically have here 0. And that means, in other words, we have probably the wrong state. So we assume the antiferromagnetic state, but presumably it is the wrong state which we have chosen. And but what we found out is that the position of this magnetic phase is very sensitive to the electron filling. That means if we add a little bit of chromium into this vanadium, or we change a little bit the lattice constant, then this peak moves up. And we did actually spin spiral calculations to find out what is actually the ground state. And you see here basically the gamma for chromium antimony, the antiferromagnetic state is the ground state, whereas for vanadium antimony it's the M point, which is basically a layered, a stripe phase. Okay, with this, I'm coming to the conclusions. I think while we have large splittings in the electronic structure, we have huge splitting of the electronic structure, which are not due to spin-orbit interaction but crystal field. The splitting in the magnon spectrum is probably not so large. And probably one has to be careful to optimize the lifetime broadening to the splitting, and this requires a little bit more work on choosing the proper materials. That is what I want to say. Thank you very much.
Thank you.
you. I have two questions, in fact. So the first one, you showed very well this magnon splitting and damping splitting. But what about the absorption coefficient? I mean, cross-section of interaction of neutrons or Rix with magnons. So is it?
No, I was not very interested in that. Yeah, I understand. Yes. But then, you know, especially if I do Rix, then I have to do something like Havercore does. I have to take the cross-section, the core hole, and things like that. That is a world in its own. If I have to do it specifically for an experiment, I will do it. But to get an overview over the altermagnets, I don't need it. It's for me sufficient to have to see how large the splitting is, how large the damping is, and then I go to the experimentalist and ask, can you measure this or can you not measure it? Is your resolution good enough?
And then the second question concerns this Billy-Nikos paper. So can you comment on the picture which you showed? Because they have only one point. I mean, they have a few points on the experimental data and they show no splitting. So can we be conclusive that it's really a magnon splitting? And is this a magnon or something else? Because Rix can give you the spectra of some other excitations.
I think they did not show the splitting, and I think this is a major thing. They understand this, that this is a problem. What I understand is, the beam time, these Rix beam lines are very rare. And you get a beam time only for a certain amount of time, and if your time is up, you have to reapply. So I guess they will continue measuring it, but they have not enough flux to describe this. Yeah. One also has to say that most of the Rix experiments are done on strongly correlated systems and gapped systems, so and metallic systems. The number of Rix experiments are not so large. So I think one needs more Rix beamlines and maybe having magnon modes which are even higher in energy so that you have a better relative resolution. I think they explained me that due to their instrumentation, the resolution itself, this 20 milli eV or so, this will not change in the next 10 years. The only thing, what we can do is maybe going higher in energy and have more flux.
Yeah, but okay, so I'm a bit familiar with that topic. So I don't think the splitting will ever be resolved in Rix, but it's exactly your point that the cross section depends actually on the incoming polarization, on the circular polarization. So if you now can show that there is a polarization dependence at a certain k vector, changes in the amplitude which actually don't tell you there's a splitting, but tell you there's a chirality there. So it is.
I had the impression you have to be on a particular beamline to do that.
Yeah, so it's very difficult to, well, the outgoing polarization cannot resolve experimentally as far as I understand, but incoming you can do that. So, but it's a very interesting topic, I think.
Thank you, Stefan. I have a question on your first conclusion. I mean, we are talking about symmetry, so I would really expect that the splitting, because it follows the symmetries of your system, it should be like that. So there is nothing, we would expect that if there is the splitting where in the Brügel zone is happening in the electronic system, you are also going to have a splitting in the magnonic system per symmetry.
Absolutely.
So I was not sure why you are putting that as a conclusion, because this is something that you expect, right?
Yes, expecting this, yes. Probably I want to say it has to have also a certain size, you know.
It has to
have a certain amplitude. Yeah, you are right. It is totally determined by symmetry. Totally determined by symmetry. For me, at the very beginning, it was not clear.
I mean, there's actually like a funny subtlety that, because if you, for example, like compare a tight binding on the chromium antimony to the linear spin wave maybe that you would do for the magnons, because the linear spin wave theory only sees the magnetic sublattice, and that has higher symmetry in some sense. So only.
You have to include so to say.
I mean, the result is that like only longer range hopping make the real symmetry manifest, and then the J's are maybe smaller than right. Yeah.
My point is, if you do it correctly,
Yes, you will.
I agree.
Yeah.
Sorry. Yeah. I agree. I mean, it's there's not a question. Yeah.
Yeah, I mean, on the experimental side, so from the neutron scattering point of view, you know, if we just do unpolarized neutrons, years ago we measured the spin excitations in LSCO, and that's 350 millieV, and the resolution is very good. So if you just wanted to see that there is a splitting, I think neutron is easier to convince yourself of that. I think polarized could be more complicated, but there are hot neutrons beamline at the ILL where you have very short wavelength neutrons. So it should be possible as well. So I think RICS, it's great techniques, but perhaps that's not necessary.
Thanks a lot, Stefan. So I want to just briefly comment on Roser's comment that that in general I agree, but magnons are bosonic representations of the groups, and the electrons are fermionic. So I can imagine some situations where this can be different. So
I have looked for this difference. I could. Now I would be interested in it.
okay. Okay. So cobalt, neop 3 sulfur 6. Did you look there into magnons?
No electrons.
So that would be my something along that lines. Cobalt neobium 3 sulfide 6 would be something to consider, but I don't know if it's the best. But we can follow.
But I think it would be.
Well, yet another one. But
I mean, it would be nice since you have all your machineries ready, probably, to look carefully
Yes.
where you have systems where the bosonic and the
Exactly.
electronic group is different.
exactly. So
That would be interesting.
That I agree that in these cases it will be one-to-one, but there might be in general cases, and I will find for you. I will try as soon as possible find for you good example. And now I have a question. So thanks a lot, Stefan. I'm really excited about seeing the different chromium antimonic siblings. Can you go to the table with the splittings? Because I wanted to ask you how you measure specifically the splitting, and if the electronic and magnonic splitting correlate with each other.
No.
And okay, no.
Oh, therefore, sorry, I didn't further mention this. Sorry, I did not mention this, but I tried to mention it. And so I said at the very beginning, at the middle of my talk, I said the splitting in the electronic structure of vanadium, is a good point, of vanadium antimony is very small. It's the smallest of the all. But if you look now at the splitting of the, where is it here? You see here the splitting. The splitting is the largest. So it's basically, it is also a thing of the crystal field. Did you know, interestingly, vanadium has the smallest magnetic moment of all the three, but it has the largest splitting. And the splitting is not directly, you have not a one-to-one correspondence between the splitting in the electronic structure and in the magnetic structure. Yeah.
I agree, but is there any trend even among the magnonic splittings itself, like that you could track it back down to some particular exchanges being anisotropic or?
So we deliberately looked at this vanadium one because we wanted to increase the anisotropic exchange. And but we overdid it a little bit at the very beginning. You know, I didn't realize that we will get this point here. But if you put a little bit of chromium in, you move it up, and then you have this large splitting. And I cannot give you the right answer yet. But there is no. We try with the data we had tried to relate is the splitting in the electronic structure and the splitting in the magnetic structure. Is it a correlation? And no. But I think you can understand the splitting. So it is not done. It is not done arbitrarily. So, yeah.
Thanks.
Stefan, again, thanks for a great talk. A follow-up on this. So you have the list of these materials. To what extent are these hypothetical, and to what extent are these real materials?
Real materials is this one and this.
Yeah, real interface that you consider. So the chromium arsenic is established to be an ultramagnetic have the altermagnetic field?
I'm not quite sure it is experimentally.
That's my question.
Yeah.
I mean, because
Yeah.
we have
But
many
I think you can
experimentals.
grow it. You can grow chromium arsenide.
We can grow it. Yes, that's why I'm
You can
asking.
grow it. Okay, okay,
No.
that's right. Yeah.
So,
But I think you can grow it, and I think so. Basically,
so from your theory perspective, it's a stable phase. This because you didn't show it. So
Yeah, it's a stable-
you tested it as a stable phase, but you don't know anything about experimental realization of this one. But it's a simple binary compound. There must be something in the materials of this one, right? I mean, people must have tried.
These two are rather common. And, so I would say this one is not rather common, but
No, but the chromium arsenic, right? There must be something on it. So it's a different structure.
I think that this phase is experimentally established in a nickel arsenide structure.
And
It is not maybe the ground state structure, but it is experiment.
but then you can maybe stabilize it in thin films or
Yeah.
okay.
But
anyway,
these other two are not experimentally established, but
so I'll ask you for references
yes.
later on.
So Yixi has started with this one, growing it in Munich, and this one I don't know. Okay. Because of course they are interested in this material because of large splitting. Yeah, so they are motivated to grow it.
Any more questions?
Thank you. Perhaps more of a comment. So you were looking at the magnitude of the electronic spin splitting to predict which materials are likely to have a large chiral splitting. But if you do it from the point of view of linear spin wave theory and you do a Heisenberg model mapping in these systems, it will come from very distant exchange couplings, which are likely to be small. So it's that's the reason why the splitting is small. But there are materials where it's already second nearest neighbor that is split. All those Lie lattice oxide selenides, they have second nearest neighbor J, J2A, J2B that may be quite different. So in those, in some cases, you can get very large chiral splitting. So for observation with limits on resolution, I think those are much more promising.
Yeah, probably we are triggered first by the idea that chromium antimony is a system that many people use for experiments. So in order to tie into this experimental community, which has samples and things like that.
Yeah, there are experiments on this. There are no experiments on the oxyselenides yet. But I mean, for experimentalists, I think that's a way to go.